All right, welcome back. Today we're doing examples of deciding and recognizing languages using Turing machines. So this is something that we've seen in class. If we want to show that a language is decidable or recognizable, we'll write a high-level description. That is a well-specified formal procedure, but not necessarily one that has to talk about the tape head or what's on the tape. And we will show that that Turing machine does indeed decide or recognize the given language. This is a companion video for lecture 9, and these examples that I'm about to show are all in CPSR on pages 207 and 208. So let's jump right into it. Our first language is going to be EQ sub DFA, and it'll accept all encoded strings. So remember, our angle brackets indicate that we are encoding some input, in particular, 2 DFAs as a string over a certain alphabet that we're not worrying about because we're at the high level. And it'll accept an encoded string if D1 and D2 are both DFAs, and the language recognized by D1 is equivalent to the language recognized by D2. So here's how we'll do this. We'll solve this using regular operations. So in particular, let's say this is the language of D1, and this is the language of D2. So what we want is for the languages of D1 and D2 to be the same. That is, we want there to be lots of stuff in the intersection, and we want there to be nothing that's in D1 but not in D2, or in D2 but not in D1. So we'll write a Turing machine that works as follows. On a certain input, the first thing we'll do is check that the input encodes DFAs, D1, D2, reject if not. So we don't always have to put that in. I like to put it in because it reminds me of what my Turing machine is doing, but it's implicit in a high-level description of a Turing machine. Next, we will build DFAs for we'll build DFAs for the complement of the language of D1 and the complement of the language of D2 using our trick for complements. I'm referring specifically to our observation from the past where we said not only are the regular languages closed under complement, but if you want to take a DFA and turn it into a DFA that recognizes the complement of the original language, you just swap the accepts and reject states. So our simulating Turing machine can certainly do that on the encoded inputs. Then, using our tricks / procedures for union and intersection. So we showed previously how to turn DFAs or NFAs. If we have 2 DFAs or 2 NFAs, we can build a DFA or an NFA for their union or for their intersection. These procedures were fully general, so there's no reason our Turing machine can't implement them. So using these tricks and procedures, we'll build a DFA for the language L prime equals the language of D1 intersection complement of language of D2. So in particular, what that is all the strings that are in this left bubble union with the language of D2 intersection the complement of language of D1. And that piece refers to everything in the right bubble. So in particular, we know that L1 is the empty language if and only if the language of D1 is equal to the language of D2. So we finish by simulating our TM for E sub DFA. That is the Turing machine that checks whether a given DFA accepts any strings. And we do it on L prime. So if L prime is empty, we accept. And if L prime is not empty, we reject. So we've used a couple of neat tricks here. We've used the fact that our Turing machine can perform well-specified procedures on finite input, in particular, taking encoded DFAs and finding their complements or their intersections or their unions, finding automata that recognize those languages. We've used that to build a DFA for L prime. And then also we've used a Turing machine that we previously specified that checks whether a given DFA accepts the empty language. And we've used it as a subroutine. By putting those two pieces together, we can decide EQ DFA. Our second example asks us to test if an input context-free grammar accepts the empty language. So our first idea might be to try generating all strings, convert to a PDA, and test all strings. The problem with these ideas is that they ask us to iterate over an infinite set, all the strings in the terminal alphabet of this grammar. So it is true that if we found a violating string, a Turing machine that worked by this rule could reject, but it wouldn't be a decider because it might run indefinitely long looking for some string that could be generated by this grammar. So we'll need to be a little bit more clever. In particular, we will specifically work up from the bottom and try to figure out whether or not the start symbol can lead to a string of all terminals. So we'll do the following. On our input, we will check to make sure the input encodes a grammar G. And then we'll do the following. We will repeat until the set of marked symbols stops increasing. We will mark all the terminals. And then we will mark all variables that produce a string of only marked symbols. Strictly speaking, I suppose we don't need to mark all the terminals inside of our loop. We can do it ahead of time. The key piece will just be iteratively marking all the variables that produce a string of only marked symbols. So what that'll do is it'll build us up from the bottom. It'll start with all the terminals, then it'll add any variables that produce strings of terminals, then any variables that produce strings of terminals and marked variables, and so on and so forth. And we'll repeat this until the marked set stops increasing. In other words, we've marked every variable that can turn into terminals. Finally, we'll accept if and only if the start variable is unmarked. So As a little illustration, suppose we had the grammar S going to AA or AOA, A going to 11 or OO or B, and B going to S. On our first step, we would mark all the terminals. That is the zeros and the ones. On our second step, we would mark the A's because it's possible for the A to produce a string of terminals or a string of all marked symbols. On the third round, we'd mark the S because it's now possible for the S to produce a string of all marked symbols. And then finally, we'd mark this B. And that effectively tells us that all of these variables can ground out in a string of terminals eventually. If this was not true, we would never be able to mark it because we'd never get there from a string of marked symbols. So that's our clever way to test if it's possible to generate a terminal string from the start symbol. Now, the third example I'm going to do today is a recognition example. So I'm going to call this language ETM complement. So ETM is just the language of Turing machines that accept nothing. ETM complement will be the language of Turing machines that accept at least one string over the input alphabet. And the program to recognize this is going to be precisely what you might expect. In particular, our Turing machine, which I'll call M0, because M is already part of the input, will do the following. On a given input, we will check that the input encodes ATM and reject otherwise. And then second, we will enumerate all strings over the input alphabet. So we'll say that S1, S2, S3, etc. is a sequence containing all strings in sigma star. And it's actually not that hard to enumerate such a sequence, right? If we have binary strings, maybe we do it in increasing order of length. So we count empty string 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on and so forth. For each I greater than or equal to 0, we are going to then simulate each string in order. So simulate strings 1 through I. Suppose we want I starting at 1 on M for I steps, except if any simulation accepts. And I claim that we're now done. This is a complete recognizer. But there are still a few interesting pieces here. So first off, why do we accept on a TM in the language? So suppose I have some Turing machine that accepts string number 1 million and it takes 1 trillion steps. Well, then by the time I get to the trillionth round of this loop, I will simulate strings 1 through 1 trillion for 1 trillion steps, and it will eventually accept. So that's a general argument that if M accepts any string, this machine will eventually accept. Why are we not just simulating the strings in order? So why don't we just go S1, S2, S3, ... and simulate S1 until it accepts or rejects? Well, it's possible that our machine accepts S2, but runs forever on S1. We don't want to get caught in an infinite loop, which is why we'll be careful by simulating strings 1 through I for I steps. That'll keep every iteration of this loop finite. So we've dodged the possibility that somewhere early in our sequence is a string that causes our input Turing machine to run forever. Finally, what happens if this runs forever? Well, it can run forever. This is a recognizer, not a decider. So unlike a decider, which is required to accept on all strings in the language and reject on strings not in the language, our recognizer is required to accept on all strings in the language and just not accept on strings that are not in the language. Not accepting can mean rejecting, but it can also mean looping or running forever. In particular, if we put into this machine a string that is not in the language, a Turing machine that accepts no strings, for example, this loop will run forever. The Turing machine will run forever, and that's valid behavior for a recognizer. I suppose if we put in a malformed Turing machine, then it would reject right in this beginning step. So that's our example of 3 high-level descriptions of Turing machines, each of which takes in an automaton or a large mathematical object as input, and each of which decides something about it using different kinds of tricks. I hope you find them useful as you're thinking about writing high-level descriptions of Turing machines, proving decidability and recognizability later in the course. So thank you for watching, and I'll see you in class.